Welcome to section 1.5 Nested Quantifiers. We are using the text Discrete Mathematics and Its Applications by Kenneth H. Rosen, 7th edition. This is Dr. Gilbert Eyabi. Math 160 Discrete Methods at Anderson University. Here are the objectives of section 1.5. We have nested quantifiers. Then we shall treat order of quantifiers. Translating from nested quantifiers into English, that's pretty exciting. And even more exciting, translating mathematical statements into statements involving nested quantifiers and translated English sentences into logical expressions. And then we would conclude with negating nested quantifiers. Let's go ahead and begin. Nested quantifiers, what are they? Well, nested quantifiers are often necessary to express the meaning of sentences in English, as well as important concepts in computer science and mathematics. For example, every real number has an inverse. Well, it should actually read, every real number has an additive inverse. It could be additive, it could be multiplicative, but for this particular example, we're talking about an additive inverse. So let's reword that sentence or that statement. It would be, for every real number x, there exists another real number y, which is the inverse of x. Now you can use this modified statement to come up with your translation into logic or nested quantifiers. For every real number x, there exists another real number y such that y is the inverse of x. What does that mean? Well, by now you should have known that x is the additive inverse of y if and only if x plus y equals 0 equals y plus x. Y is the multiplicative inverse of x if and only if x times y equals 1 equals y times x. That's a whole different subject, which we would probably touch again at some point when we start doing inverses. But for now, just know that y is the additive inverse of x if x plus y equals 0. And the same thing, that means y plus x equals 0, but we will just stick with x plus y equals 0 since there is commutativity in addition. Okay, so let's go ahead and translate this into logic using quantifiers and predicates. For every x, for every real number, there exists a y, there is another real number, such that. At this point, we will not actually use the word such that, but that's where we're going. Once we start dealing with proofs, we would actually put such that, but we'll represent it with s dot t, okay? But the parentheses would mean such that. That is your predicate right here. So for every real number x, there exists a real number y such that x plus y equals 0. You could also say y plus x equals 0, and that would be good. So x and y are from the set of real numbers. That is your domain. Now you could also write this in a very complicated way, which I would not advise that you go this route. It would be for every real number x, qx is true. Qx now would be the statement, there exists a y such that p of xy is true. And p of xy would be x plus y equals 0. That's just a lot. So let's stick with this. Okay, let's think of nested quantification. What's actually nested quantification? Let's look at it like we did before. We're looking at nested loops. For every x, for every y, what does that mean? It means if I pick an x, I loop through all the y's and check out the predicate p of xy, whether it's true or not. I pick another x, I loop through all the y, pick another x and do the same. If I find even one combination of x and y such that p of xy is not true, then the entire nested quantifier and predicate would be false. Or we simply say the entire statement is false. So you loop through the values of x. At each step, you loop through the values of y. If for some pair of x and y, p xy is false, then for every x, for every y, p of xy is false, and both the outer and inner loop would terminate. But for every x, for every y, p of xy is true if the outer loop ends after stepping through each x, i.e., I take the first x, loop through y, the second x, loop through y, the third x, loop through y, and if I go through all the x's and I do not find a pair xy such that p of xy is false, then I conclude that for every x, for every y, p of xy is true. Again, you can only do that if you're dealing with a domain that has finitely many elements. If you're dealing with an infinite domain like the set of real numbers or the set of integers, there is no way you can do that. Okay, so we're going to learn how to prove that for every x, for every y is true using inferences, or actually different proof techniques, which we would learn in 1.7 and 1.8. Now, what about this statement right here? What is the truth value of for every x, for every y, x plus y equals 7? What does this mean? For every real number x and for every real number y, x plus y equals 7. Interesting. So just start off by picking some real number x and look through all real numbers y and see if there is even one situation where x plus y is different from 7. So why don't you take x to be 10 and just start looping through y and pick y to be 5. 10 plus 5 is different from 7, so this statement is false. What about for every x, there exists a y such that x plus y equals 7? That means I start off with my first x, I pick an x, I loop through the entire domain y, where y comes from. Can I find a y such that x plus y equals 7? If my domain is the set of real numbers for both x and y, would that work? Well, that means I can solve for y, which will give me 7 minus x. So whatever x is, y will be 7 minus x. So that's good. Now what about there exists x, there exists y such that x plus y equals 7? There exists x, there exists y such that x plus y equals 7. There's a particular x and there is a particular y such that x plus y equals 7. What's the truth value? What about there exists x for every y such that x plus y equals 7? There is a particular x that it doesn't matter which y I pick. That x plus that y must give you 7. Doesn't sound good at all. Is there a particular x that it doesn't matter which y I pick? When I add the y to that x, I always get 7? Don't think so. But you go ahead and investigate these 4 and see which ones are true and which ones would be false. Now, to see if for every x there exists y, p of xy is true, I pick my x and I loop through y, and I'm looking for just one value of y for which p of xy is true. Once I find that value, I'm done. For every x there exists y, p of xy is true. But if I loop through all the x in my domain and I cannot find a y such that p of xy is true, then I can conclude that for every x there exists y, p of xy is false. For every x there exists y, p of xy is true if the outer loop ends after stepping through each x. If the domains of the variables are infinite, then this process cannot actually be carried out. We have to find a different way to verify that for every x, for every y, for every x there exists y, there exists x for every y, and so on and so forth is true or false. Now let's talk about order of quantifiers. Examples. Example 1. Let p of xy be the statement x plus y equals y plus x, and let u be the set of real numbers. That is our domain or our universal set. Then, what is the truth value of for every x, for every y, p of xy? And for every y, for every x, p of xy? Does the order here matter? For every x, for every y, for every y, for every x? As a matter of fact, the order here does not matter. For every x, for every y would be the same as for every y, for every x. They would have the same truth value. But look at example 2. Let q of xy be the statement x plus y equals 0. Assume that, again, our universal set or our domain is a set of real numbers. Then for every x, there exists y, and there exists y for every x are two very different statements Therefore, for every x there exists y, q of xy is very different from there exists y for every x, q of xy. The first statement is true, but the second statement is false. What the first statement states is this: for every real number x, I can always find a y, which is also a real number, such that x plus y equals 0. As a matter of fact, y is going to be the additive inverse of x. So that statement is true. But what does the second statement mean? It means there exists a real number y such that irrespective of the value I chose for x, x plus y equals 0 all the time. That is not true. So order matters, order of quantifiers. Let's look at a few questions on order of quantifiers. Example 1. Let U be the set of real numbers, that is our domain, the universal set, and define our predicate P of xy to be x times y equals 0. Number 1. What is the truth value of the following? For every x, for every y, P of xy. For every real number x and for every real number y, x times y equals 0. That's not true. That's false. Go ahead and give a shot at this order 3. Don't look at the answers. Just figure out what you think the answer would be by looking at it, and then we would discuss the answer. Take a few seconds. Very good. Now let's look at the second one. For every x, there exists y such that P of xy is true, such that x times y equals 0. If I pick any real number x, there is always another real number y such that x times y equals 0. Yes, that real number y is just 0, so that's true. There exists a real number x such that irrespective of the y I pick, x times y is 0. Yes, that x will be 0. There exists a real number x and there exists a real number y such that x times y equals 0. Yes, take x equals 0, y equals 0, and we're good. Okay, let's move on to some more questions on order of quantifiers. Example 2. Let U be the set of real numbers, our universal set, our domain. Define P of xy to be x divided by y equals 1. Of course, the assumption here would be that y is different from 0. And that would come in when you start answering the questions. Because if you see for every y, you have to be very careful. Because if y equals 0, that's slightly undesirable in the math world. Okay, let's proceed. What is the truth value of the following quantifiers? For every x, for every y, P of xy. For every real number x and for every real number y, x divided by y equals 0. No way. That's not true. Take a few seconds and look at 2, 3, and 4. For every real number x, there exists another real number y such that x divided by y equals 0. Number 2. For every x, there exists a real number y such that x divided by y equals 1. For every x, there exists a y. It doesn't matter which x I pick, there is always a y such that x divided by y equals 1. It almost sounds like that should be true, except that we're dealing with a set of real numbers and 0 is in that set, so x could be 0. If x is 0, can I find a y such that 0 divided by y equals 1? No, that's false. And check and see that number 3 is false and number 4 is true. There is a real number, x, and there is a real number y such that x divided by y equals 1. Yes, take x to be 5 and take y to be 5. Then 5 divided by 5 equals 1. As a matter of fact, 5 divided by 5 could be seen as 5 times 1 over 5. And 1 over 5 is the multiplicative inverse of 5. That is story for another time. Quantifications of two variables. So we have for every x, for every y. When is it true? P of xy is true for every pair xy. When is it false? If I can find a pair xy for which P of xy is false. And that follows for the same for every y, for every x. For every x, there exists y. There exists x for every y. There exists x. There exists y. There exists y. There exists x. So here you find the situations when these would be true and when this would be false. And so you need to know this so that you can tell when there exists x for every y, P of xy is false. When would that be false, for example? This means there is a particular x from our domain such that irrespective of the y I pick from y's domain, p of xy is always true. So your predicate is very important. You have to look at the statement of the predicate. Is it true that there is one unique x, one particular x, such that irrespective of the y I pick, p of xy is always true? If not, it's false. Now let's proceed and do some translation. You realize that when you're translating, my advice would be to first of all come up with a draft and then refine the draft and come up with something that is more everyday English. Let's start with this example. Translate the following statement. For every x, watch your parentheses very carefully. C of x or there exists, realize that all of these fall under this parentheses, C of y and f of xy. C of x means x has a computer. F of xy means x and y are friends. And the domain for both x and y consists of all students in your school. So here is a draft translation. For every student x, okay, I'm just reading this exactly the way it is. For every student x, C of x, x has a computer or there exists another student y such that, okay, remember I said that when you see the parentheses, that is such that, though we'll not use it very often now, but in our draft translation, we can put it such that C of y, C such that C of y, that means y has a computer and x and y are friends. Or we can say for every student x, either x has a computer or there is another student y who has a computer and is x's friend. X and y are friends. So let's refine the translation. It now becomes every student in your school has a computer or has a friend who has a computer. Now in a test, I do not expect everyone to come up with the exact same sentence, but I expect you to be very close, to come up with some variation of the same statement. Let's look at the second example. This is probably more exciting. There exists x for every y for every z. You see, I have my entire left. Look at where the parentheses are. It opens right here. Look at where my parentheses are. I have f of xy and f of xz and y different from z right there implies this. So I have the entire left component implies the right component, and then I have there exists for every. So let's give you the draft translation. There exists a student in your school such that for any other two students who are distinct, if, remember this means if then, implies, means if then. If x and y are friends and x and z are friends, then y and z are not friends. Okay, let's try it again. There exists a student in your school such that if y and z are two other students and are distinct and x and y are friends, x and z are friends, then y and z are not friends. So I have it here as there is a student in the school x such that for any other two distinct students y and z, if x is a friend to both y and z, then y and z are not friends. And we can refine this as there is a student, none of whose friends are also friends with each other. Again, I do not expect you to come up with very beautiful, nice, refined translation like this all the time, but I expect to see your translation as close as possible to the refined translation. In other words, your translation has to be an actual translation of the logic statements. Okay, what about translating mathematical statements into predicate logic? The sum of two positive integers is always positive. How do I translate the sum of two positive integers? Now, the sum of two positive integers means for every x, x greater than 0, for every y, y greater than 0, x plus y is greater than 0. Okay, so you see my draft. So I rewrite the mathematical statement in a form that could easily be translated into predicate logic. for every x, x bigger than 0, for every y, y bigger than 0, x plus y is greater than 0. And that leads me to, for every x, for every y, if x is greater than 0 and y is greater than 0, then x plus y is greater than 0. That was easy and straightforward. Translating mathematical expressions into predicate logic. Of course, in this case, our domain would be the set of integers, and that will be the domain for x and the domain for y. Now, what about translating English into logical expressions or into predicate logic? Example, use quantifiers to express the statement, and when we say quantifiers, we mean quantifiers and predicates, all of those put together, we just call them quantifiers. So let's use quantifiers to express the following statement. There is a woman who has taken a flight on every airline in the world. There is a woman who has taken a flight on every airline in the world. So what are some things you see here? Number one, there is a woman, there exists W, who has taken a flight, there exists a flight F, on every airline, for every airline. Now, how do I put all of these together? Now, let's define the following predicates. PWF, W has taken flight F. QFA means F is a flight on airline A. Then the domain for W would be all women, the domain for F would be all flights, and the domain of A would be all airlines. Now I can translate this as there exists a woman, for every airline there exists a flight, such that the woman has taken the flight and the flight is on some airline. So there exists W for every A, there exists F such that, remember there's always a such that, P of WF and Q of FA. The translations might be a little different from student to student, but I should be able to see very clearly from your translation that you are actually translating the statement given. Okay? Questions on translation from English to predicate logic. Choose the obvious predicates and express in predicate logic. Number one, brothers are siblings. We have brothers, we have siblings. So you may want to use BXY to mean X is a brother to Y, or X and Y are brothers. You may want to use SXY to mean X and Y are siblings. Then you want to rewrite this statement, brothers are siblings. How would you rewrite that? If X and Y are brothers, then X and Y are siblings. Now it's very easy to translate that into predicate logic. Okay? Example 2. Siblinghood is symmetric. So how do you rewrite that in a form that is easily translatable to predicate logic? If X is a sibling to Y, then Y is a sibling to X. So that becomes for every X, for every Y, if X is a sibling to Y, then Y is a sibling to X. What about everybody loves somebody, where LXY means X loves Y? Everybody loves somebody. For every X, of course, your domain here will be the set of all people in the world, over 7 billion people. So for every X, it doesn't matter what X I pick, there is always a Y such that X loves Y. There is somebody who is loved by everyone. There is someone who loves someone. Everyone loves himself. You would be getting quite some number of examples to play with in class and also for your homework and maybe even your test. These examples are beautiful. Okay, we will conclude this section with negating nested quantifiers. And like I mentioned before, when you negate quantifiers, for every changes to there exist changes to for every, and the predicates are negated. Okay, that's it. As easy as that. So view the negation sign as water, oil, some liquid that seeps through the quantifiers right down to the predicate. As it seeps its way through, it changes all for every signs to there exists, changes there exist to for every until it gets to the predicates. And it hits the predicates and negates all the predicates. And if there is any and sign, it becomes or. If there is any or sign, it becomes and. Of course, if there exists sign and if and only if sign, you have to go back to negating the different logic symbols. Okay, as easy as that. For example, there exists W, for every A, there exists F. Okay, for now, let's just ignore the predicate. If I were to negate this, what would I get? There exists becomes for every W, for every A becomes there exists A, there exists F becomes for every F. Now I go to my predicates. I will negate P of WF, I would negate Q of FA, and my AND becomes all. So my final answer would be there exists becomes for every becomes there exists becomes for every, F stays. Now P of WF becomes not P of WF and becomes all, QFA becomes not Q of FA, and that is the negation of that nested quantifier. Now, can you translate this back to English? It could be a little challenging, but as I mentioned before, come up with a draft and then refine the translation. And the refined translation would be, for every woman, there is an airline such that for all flights, this woman has not taken that flight, or that flight is not on this airline. Interesting. Some questions about quantifiers. Let's go ahead and do this. Can you switch the order of quantifiers? Be very careful. Would this be a valid equivalence for every x, for every y, p of xy? For every y, for every x, p of xy? Yes, this would be a valid equivalence. The left and the right side would always have the same truth value. The order in which x and y are picked does not matter. But you have to be very careful when the quantifiers are different. For every x, there exists y, p of xy. Is that equivalent to there exists y for every x, p of xy? No. The left and the right side may have different truth values for some propositional functions for p. Why don't we try x plus y equals 0? For p of xy, with u being the integers, the order in which the values of x and y are picked does matter. Okay? So you do not switch quantifiers unless you know exactly what you're doing. If you're dealing with for every, we're good. Once you're dealing with different quantifiers, don't. Can you distribute quantifiers over logical connectives? Yes and no. It depends. For example, for every x, P of x and Q of x is actually equivalent to for every x, P of x and for every x, Q of x. So I just distributed my quantifier over and. What about over all? And even more exciting, what about over the implication sign? For every x, P of x implies Q of x. Is that equivalent to for every x, P of x implies for every x, Q of x? No. The left and the right side may have different truth values. Pick x is a fish for P of x and x has scales for Q of x, with the domain of discourse being all animals. Then the left side is false because there are some fish that do not have scales, but the right side is true since not all animals are fish. So we have to be very careful. It's yes and no depending on what the connectives are. That brings us to the end of section 1.5, nested quantifiers. Now we go to section 1.6, rules of inferences, and then move on majestically to sections 1.7 and 1.8, where we start looking at proofs and some methods of proofs. I look forward to seeing you there. Thank you and God bless you.